In this video, we will discuss about the ionic product of water, pH and buffer solution. First, let us discuss about the ionic product of water, denoted by Kw. Now, let's write an expression for the self-ionization of water. So, the expression for self-ionization of water is H2O liquid ionized to give H plus OH minus, or we can also write it as H2O liquid plus H2O liquid will give H3O plus aqueous plus OH minus aqueous. And in the second expression, we can see that there are two H2O molecules on the reactant side, out of which one will act as a Bronsted acid and the other will act as a Bronsted base. So suppose this H2O acts as a Bronsted acid, then this will act as a Bronsted base. You know what are Bronsted acids? Bronsted acids are proton donors and Bronsted bases are proton acceptors. Now in the product formed, we know that we have H3O plus, in which there is one extra H plus ion, and we have the other product as OH minus, in which there is one less H plus ion. So we can say H3O plus is the conjugate acid of the base H2O and OH minus is the conjugate base of the acid H2O. Okay, so this expression can also be written for the self-ionization of water. Now I told you we are going to get an expression for Kw. So first we are going to write the expression for the equilibrium constant Kc. And suppose I give this as equation number 1 and this as equation number 2. I am going to write the expression for equilibrium constant Kc using equation number 1. So you know how to write the expression for Kc, equilibrium constant. Kc is equal to, this is for equation number 1 I am writing, product of molar concentration of products. We have H plus and OH minus ion as the products by molar concentration of reactant, which is H2O. And we know that the concentration of H2O in liquid state is taken as 1 because H2O is weakly dissociated. So concentration of H2O is taken as 1. Now this 1 is incorporated along with Kc. It gives rise to a new constant denoted by Kw. So again I am going to rewrite this expression Kc in terms of Kw, and the expression will be Kw is equal to concentration of H plus into concentration of OH minus. So this is the expression for ionic product of water, and we know by H2O that concentration of H2O is taken as unity 1. So the expression for the ionic product Kw of water is concentration of H plus into concentration of OH minus ion. Or you can write for the second equation which we have written, equation number 2, the expression for ionic product as Kw, instead of H plus we will have concentration of H3O plus into concentration of OH minus. So how can we define the term ionic product of water? Ionic product of water is defined as the product of molar concentration of H plus and OH minus ions. So that is the definition for the ionic product Kw of water. Now this Kw takes different values at different temperature. Now the value of Kw, we are going to find what is the value of Kw at 25 degrees Celsius, or 25 degrees Celsius in Kelvin scale is 298 Kelvin. And it is found that at 25 degrees Celsius H2O molecule will dissociate to give equal number of H plus and OH minus ions. So we can say at 25 degrees Celsius the concentration of H plus ion will be equal to the molar concentration of OH minus ions. And it was found that the concentration of H plus ion at 25 degrees Celsius was found to be 10 raised to minus 7 molar. So, you know that at 25 degrees Celsius, water dissociates to give equal number of H plus and OH minus ion. So, if the concentration of H plus ion is 10 raised to minus 7 molar, then at 25 degrees Celsius, the concentration of OH minus ion will be also the same, that is 10 raised to minus 7 molar. Now, we can get the value for Kw. Kw is equal to concentration of H plus into concentration of OH minus, which is equal to, concentration of H plus is 10 raised to minus 7 into 10 raised to minus 7, which is equal to 10 raised to minus 14 molar square, capital M square. So, this is the value of Kw at 25 degrees Celsius. And I told you Kw, ionic product of water, that value changes with change in temperature. So, this is the value that we get at 25 degrees Celsius or 298 Kelvin. That is, Kw is equal to 10 raised to minus 14 molar square. Now, let us see the effect of temperature on ionic product of water. So, next, effect of temperature on Kw. Kw denotes the ionic product of water. Now, we know that the Kw, or as temperature increases, Kw increases. Now, why the ionic product of water increases as temperature increases? Because we know that as temperature increases, more H2O molecule will ionize or dissociate into H plus and OH minus ions. So, the concentration of H plus and OH minus ions increases, so Kw value also increases. Okay. So, that is the effect of temperature on the ionic product of water. Now, the next thing that we are going to discuss is, we can distinguish acidic, neutral and basic solution from the relative concentration of H3O plus and OH minus ion. That is, if you know the concentration of H3O plus and OH minus ion, we can predict whether the given solution is acidic, basic or neutral. Again, we know that for pure water at 298 Kelvin or 25 degrees Celsius, we know that the concentration of H3O plus is equal to concentration of OH minus, which is equal to 10 raised to minus 7 molar. Okay, and we know that we know the equation for the self-ionization of water, that is H2O plus H2O gives H3O plus OH minus. Now, suppose to this reaction which is at equilibrium, I am going to add more H plus ion. Means when I add more H plus ion, it means the concentration of H3O plus will be greater than 10 raised to minus 7 molar, or it will be greater than concentration of OH minus, and we know the equilibrium is disturbed when I added more H plus ion. So, what will happen according to Le Chatelier's principle? According to Le Chatelier's principle, the reaction will take place in backward direction, preventing the ionization of water. Okay, now in this case, we know that the concentration of H plus is more than concentration of OH minus. So, we can say that if the concentration of H3O plus is greater than concentration of OH minus, then we can say that the solution is acidic in nature. Now, suppose I add alkali or a base to this reaction at equilibrium, then what happens? The concentration of OH minus ion will be greater than concentration of H3O plus. Again the equilibrium is disturbed, so according to Le Chatelier's principle, the reaction will proceed in backward direction, thus preventing the ionization of H2O. So now when I added more amount of alkali, what happened? The concentration of OH minus will be greater than concentration of H3O plus. In this case, the solution will act as a basic solution. Now, at equilibrium, we know that the concentration of H3O plus will be equal to concentration of OH minus, and in this case, the solution will be neutral. So, depending on the concentration of H3O plus and OH minus, we can predict whether the given solution is acidic, basic or neutral. If the concentration of H3O plus is greater than OH minus ion concentration, then the solution is acidic. If concentration of H3O plus is less than concentration of OH minus, the solution is basic. If concentration of H3O plus is equal to concentration of OH minus, the solution is neutral. So, we completed the ionic product of water. Ionic product Kw is defined as the product of molar concentration of H plus and OH minus ions. Now next let us discuss about the pH scale or pH. So next we have pH. Now the hydronium ion concentration. Hydronium ion means H3O plus. We know that H plus is very reactive, so immediately the H plus formed will react with H2O and form H3O plus, which is called the hydronium ion. So hydronium ion concentration in molarity is expressed on a logarithmic scale known as pH scale. Now how can you define the term pH? It is defined as the negative logarithm of concentration of H plus ion, or you can say concentration of H3O plus ion. So this is the definition for the pH. It is defined as the negative logarithm of concentration of H plus ion. Now when we write the expression, we can write it as pH is equal to minus log concentration of H plus, or minus log concentration of H plus can also be written as log 1 by concentration of H plus. So negative log concentration H plus is same as log 1 by concentration of H plus. Now we know that the pH of pure water is equal to 7. pH of pure water is equal to 7. Now let's see how did we get that 7 as pH of pure water. We know that at 25 degrees Celsius or 298 Kelvin, the concentration of H plus ion on self-ionization of water is 10 raised to minus 7 molar. So we are going to substitute in the expression for pH the concentration of H plus ion. So the expression for pH is pH is equal to minus log concentration of H plus, which is equal to minus log concentration of H plus is 10 raised to minus 7. Now here you have to study this log m raised to n power is equal to n log m. So this is the power law which you learn in logarithm. So log m raised to n is equal to n log m. So here we can write minus log 10 raised to minus 7 as minus, then log 10 raised to minus 7 will be minus 7 log 10. Now log 10 is equal to 1. The value of log 10 is equal to 1. So we will have minus of minus 7 which is equal to 7. So this is how you get the pH of pure water as equal to 7. Okay. Now, we know that if the solution is acidic, then pH will be less than 7, then that solution will be acidic in nature, and if pH is greater than 7, then that solution will be alkaline or basic in nature. So this is regarding the pH. Now next, let us see the relation between pH and pOH. So next heading we have relation between pH and pOH. Now we know what is the expression for pH. pH is minus log concentration of H plus ion. So we have pOH, we can write as minus log concentration of OH minus ion. Now we know that since concentration of H3O plus into concentration of OH minus is equal to Kw, that is the ionic product of water, and its value is equal to 10 raised to minus 14 molar square at 25 degree Celsius. We know this. Ionic product of water is 10 raised to minus 14 molar square at 25 degrees Celsius. Now, I am going to take negative logarithm of this ionic product of water, that is this expression, concentration of H3O plus into concentration of OH minus is equal to Kw. So I am going to write, or I am going to take the negative logarithm for this expression. So I will be writing it as minus log concentration of H3O plus. Now here it is the product, that is concentration of H3O plus into concentration of OH minus. When you write it taking logarithm, if the product will be written as sum. So we will write minus log concentration of H3O plus minus log concentration of OH minus is equal to minus log Kw, which is equal to minus log 10 raised to minus 14. Now, this is the product rule, that is we have a rule like this, that is log m n will be equal to log m plus log n. Okay, so this is the product rule. So that's what I have written here, addition, minus log H3O plus minus log concentration of OH minus. Now you know that minus log concentration of H3O plus is our pH. So I am going to write instead of minus log concentration of H3O plus as pH. Then minus log concentration of OH minus is pOH. So plus pOH is equal to minus log Kw will be pKw, and its value, we know that minus log 10 raised to minus 14 value is 14, so which is equal to 14. So this is the relation between pH and pOH, that is pH plus pOH is equal to pKw, which is equal to 14. Now next we are going to see relationship between Ka and Kb, or pKa and pKb. So next, relation between Ka and Kb, or pKa and pKb. Now Ka is called the acid dissociation constant and Kb is called the base dissociation constant. Now pKa will be the negative logarithm of Ka and pKb will be the negative logarithm of Kb. Okay, so we are going to get a relation between Ka and Kb, or pK and pKb. So for this, let's consider a weak acid HF, hydrofluoric acid HF, and HF will dissociate as H plus F minus, and we can write the expression for Ka. Ka will be equal to concentration of H plus into concentration of F minus divided by concentration of HF, and give this equation number 1. Now all the reagents and ions are in aqueous state. Now you know that F minus is the conjugate base of HF. So let's write the ionization of F minus in water. So next I am going to write the ionization of the base F minus. F minus plus H2O, we get OH minus plus HF. Now this is aqueous, H2O is liquid, OH minus aqueous, HF is aqueous. Now let's write the expression for Kb, because F minus is base. So we have to write the base dissociation constant. Kb will be concentration of OH minus into concentration of HF divided by concentration of F minus. Concentration of H2O in liquid state is taken as 1. And let's give this equation number 2. Now, when you multiply Ka into Kb, equation number 1 and equation number 2, we have Ka into Kb, and which is equal to, when you multiply, you can see all the terms get cancelled except H plus and OH minus, and so the expression will be Ka into Kb will be equal to concentration of H plus into concentration of OH minus, which is equal to the ionic product of water, that is equal to Kw. Now I am going to rewrite this expression as Ka into Kb is equal to Kw. So this is the relation between Ka and Kb. Ka into Kb is equal to Kw. Now I am going to take the logarithm for this expression. Ka into Kb is equal to Kw. So when I take logarithm, I am going to write it as log Ka plus log Kb is equal to log Kw. Or when I take negative logarithm, it will be minus log Ka plus minus log Kb is equal to minus log Kw, and we know the value is minus log 10 raised to minus 14. Kw value at 25 degrees Celsius will be 10 raised to minus 14. So minus log Ka can be written as pKa plus minus log Kb is pKb is equal to pKw, which is equal to 14. So this is the relation between pKa and pKb. Okay, now the relation between Ka and Kb is Ka into Kb is equal to Kw. The relation between pK and pKb is pKa plus pKb is equal to pKw, which is equal to 14. Now you can predict the strength of an acid or a base depending on its Ka, Kb or pKa, pKb value, and the rule is this, that is, higher the value of Ka or smaller the value of pKa, stronger is the acid. So this is for the strength of acid. Higher the value of Ka or smaller the value of pKa, stronger is the acid. Now for base we can say, or we can give the strength of a base in terms of Kb and pKb. So the same rule applies here, that is, higher the value of Kb or smaller the value of pKb, stronger is the base. because pKb is the negative log, minus log Kb. So higher the value of Kb or smaller the value of pKb, stronger is the base. So this is something very important. If you are given the Ka or Kb, pKa or pKb value, you can predict whether it's a strong acid or a strong base, or a weak acid or a weak base from the values. And these are the rules for assigning the strength or strength of a base or an acid. That is, higher the value of Ka or smaller the value of pKa, stronger is the acid, and higher the value of Kb or smaller the value of pKb, stronger is the base. So this is our pH and the relation between Ka, Kb, pKa, pKb. Now next we have buffer solution. So next topic is about buffer solution. Buffer solutions. Now what are buffer solutions? We know many body fluids like blood or urine, they have a definite pH value, and any deviation in their pH indicates the malfunctioning of our body. Now the control of pH is very important in many chemical and biochemical processes. Now what do you mean by a buffer solution? A solution which resists change in pH on dilution or with the addition of small amount of acid or alkali are called buffer solution. Means there will not be any change in the pH value of this buffer solution. That is, a solution which resists change in pH on dilution or with the addition of small amount of acid or alkali is called a buffer solution. Now we have two types of buffer. One is called acidic buffer and the second is basic buffer. Acidic buffer. And example you have to study for acidic buffer: mixture of acetic acid and sodium acetate. You know the formula of sodium acetate. Sodium acetate is CH3COONA. This is an example for acidic buffer. And this acidic buffer, they act as a buffer solution around pH 4.75. Now the second type of buffer solution is basic buffer. Basic buffer. An example for basic buffer is mixture of ammonium chloride and ammonium hydroxide, and they act as a buffer around pH 9.25. So these are the two types of buffer solution. So with this we complete our ionic product of water, pH and buffer solution. Thank you.